So let me tell you what all the things I'm going to cover in today's this session. First one thing is overview of the quantum cryptography, then basics of quantum mechanics. I think this basics of quantum mechanics you might have learned in the last 5 days also. So we'll see more on the principles of quantum cryptography and how these principles were being used in the different algorithms. Then we will see some quantum key distribution algorithms, and we'll see with one particular example. Then the benefits and challenges, some applications, what all are the future trends, and some question answering and thanking session and some references. So we'll start with the basic thing, what exactly the cryptography it is. You might be all might be aware that the basic cryptography stuffs we have seen in the computer networks or information security, but kind of the topics one. So before going for the quantum cryptography, we must have at least a basic, you can say, the understanding of what exactly the cryptography it is. So there are actually three types. We can say in the cryptography, the traditional cryptography, it is a symmetric key cryptography, or you can say the public, and second one is a public key cryptography. These all are most of the attendees over here might be aware all what exactly the symmetric key cryptography, what is the working and procedure in the symmetric key cryptography, and also the public key cryptography, like how this is working, how the public key and private key is getting generated, and the encryption and decryption process, and all this particular regarding the asymmetric key cryptography. So I'm not going to much focus on this traditional cryptography part, because it is, I think, you all are aware, and I'm considering that you all are aware about this traditional cryptography concepts, and I'm moving forward for the quantum cryptography. Right. So first of all, I will see what exactly the quantum cryptography it is. So basically, if I'm going to compare this quantum cryptography with the traditional cryptography, we can see in the traditional cryptography, what we have, which involves the lots of complex mathematical computations, lots of the formulas, lots of the algorithms are used to more secure the encryption process, the key handling process one. But here in the quantum cryptography, we use the principles of quantum mechanics to encrypt the message. So we'll use in the quantum cryptography the principles of quantum mechanics. So might be you all are aware about what exactly the quantum mechanics it is. To encrypt the message and send it over the quantum network or the channel, so that the receiver can decrypt it and get the original secure message one. So this particular makes the quantum cryptography much more secure. Perhaps most of the theoretically we can call this is as an unhackable one, or you can say the unbreakable. Okay, so we'll move to the next one, the basics of quantum mechanics. I think I'm not going to much more focus on this quantum mechanics, because in the last few days you might have knows these all particular stuff like superpositioning. Sorry for the disturbances. So you might have seen the superposition and entanglements and quantum qubits or quantum bits. So I'm going to consider this as all you are aware, and we'll move forward for the what exactly the cryptographic terms it is. So in the cryptography, what exactly we mean is we are sending one particular message from the sender, and a receiver will receive that particular message. But what will happen if anyone who is listening your conversation, who is listening your information, or who is listening or tampering that particular information, right? So to make a secure, what we'll do is we'll use a different kind of the methods or algorithms to save or to secure our communication, right? So like as in the traditional cryptography, we use the symmetric key and public key methods to secure our communication. Here, we in the quantum cryptography, we use some of the principles. Based on these principles, we can secure or we can provide one particular path to secure our, you can say, the information or the message, right? So out of it, first one is Heisenberg's uncertainty principle. We'll see these all principles a little bit more in detail in the later on slides one, or in upcoming presentations one. Then we have the quantum entanglements and no cloning theorem one. So basically, these are the three important terms, or you can say the principles we are going to use in the most popular algorithms in the quantum cryptography. Right. So first one is I'm just giving a little bit short descriptions because we will see the practical use of this particular principles later on during the example. Okay. So quantum cryptography, this is a principle is used to create the secure communication channels as measuring the quantum states inherently disturbed states, which ensures the detection of a eavesdropping attempt. Most frequently, this particular uncertainty principle we use for detecting the eavesdropping. Second one is quantum entanglements. When quantum particles are entangled, I think the entanglement and this particular stuff you are aware in the last sessions one. So their states are strongly correlated, meaning that the changing of one particle affects its entangled partner instantaneously. So this property is used to create a secure connections between sender and receiver, ensuring that no one else can intercept the entangled states. That is, it is mostly been used to see whether any one or any the system in between your communication is monitoring or tampering your data or not, right? So the third one is this particular no cloning theorem, or this kind of this principle is used almost in all algorithms because this is closely related to the properties of the quantum mechanics. So this principle states that the unknown quantum state cannot be cloned, making it possible for eavesdroppers to create exact copies of transmitted quantum states. So this will what we can say, it will prevent the eavesdroppers to attack on your data or tamper your data, right? So this is effectively prevents the wire tapping attacks one. So we'll see one of the algorithms in detail because if we can go only one algorithm, then we can able to clearly understand what exactly and how exactly these particular algorithms, quantum cryptography algorithms are going to be work. And based on that particular one algorithm, we can easily get understand the other algorithms also. Right. So just a minute. So in the quantum cryptography, we have two major protocols. Namely, we have the BB84 and the. Hello, am I audible? Hello.
Yes, sir. You can
Yes, sir. Audible.
Okay. Thank you. So
yes, sir.
So here we are going to look into these two major algorithms. One is BB84 and second one is ECART91. Both these algorithms are work on the different quantum principles which we have learned here. These all principles. So these both algorithms are works on a different quantum principles, quantum cryptography principles. So first one, we'll see in detail what exactly the BB84 protocol it is, or how this protocol is going to be work, what exactly it is securing your can say the communication, or how the QSD is going to be work here. So here it is the first and one of the most widely studied quantum key distribution. protocol. Most of the time we have some other algorithms one also, but it is most old and most widely used quantum key distribution algorithm. So during my next presentations, I have taken a use of this only BB84 algorithm to detail understand how the whole process is going to happen. Right. So historically talking about, it was proposed in 1984. That's why this 84 is written in the name of the algorithm, and it has been proposed by the Charles Bennett and Gilles Bressard. So, uh, considering the surnames of these two and the year of proposed 84, so it has been defined the name as a BB84, and this is most popular quantum cryptography algorithm. The protocol enables two parties. Now, throughout this particular, now onwards, throughout this whole particular presentations, I'm going to use two parties, sorry, two particles, or sorry, two parties, which are, one is the sender and receiver, and mostly I'll call the sender as Alice and receiver as Bob. Okay. Uh, the the protocol enables two parties, typically Alice and Bob, to securely share the cryptographic keys over the insecure communication channel, even in the presence of eavesdropper. Commonly, we'll use EV for the eavesdropper. So from this slide onwards, we'll use these three names: Alice, Bob, and Evie. Alice is represents as a, she is the sender. Bob is a receiver, and Evie is a eavesdropper. Right. So before going for these protocols in detail, we'll see what are the major or key differences between this BB84 and E91, ECAT91, this particular protocol. So there is a difference in the principle, that is use of single photons and polarization states. Uh, Here in this particular algorithm, BB84, we use a single photon and the some polarization mechanism. It is again I'll like more explain it during when we are going to start with this BB84. But for the time being, just remember that we use a single photon and the polarization states one. And here it is rely on the entanglement photon pairs. So in the entanglements, we have discussed just now that the particles are entangled and uh, uh, the states are strongly correlated. So that means changing the one particle, it affects the entangled partner one also instantaneously. So this particular algorithm, or I can say that this particular methodology works on the entanglement photon pair. Talking about the implementations, it involves the transmission of an individual photon, and here it involves the distribution of entangled photon pairs. So this is just what the key differences what we have. Again, we have the more the detailed the differences also, but for now, for the sake of understanding of these two algorithms, this is I think it's enough one. So underlying principles, it is uses the single photon and polarization states, and it relies on the entangled photon pair. And in the implementation, it involves the transmission of individual photons and it involves the entangled photon pairs. Okay. So talking about the quantum key distribution, as I said, this for the quantum key distribution, we use these two protocols, E91 and BB84 protocols. So we'll see in detail uh, the what this particular protocol includes, how this is going to work, and how we can able to compare the keys or detect eavesdropping. So we'll talk about this BB84 protocol, which includes the sending of photons with random polarization, measuring using the random basis. So how these bases are getting calculated, that also I'm going to tell. Then publicly comparing the bases and detecting the eavesdropping. These all particular steps are getting included into the BB84 algorithm. So uh, before starting, I just want to show you one particular. Not able to start. Okay. So what we saw in this particular video is there is one particular hello. Yes, sir, audible. You're audible. Yeah, there are two receivers, one and the Alice center and Bob is receiver one. Now, what happens? How we are going to uh, adjust the detector for photon detector? Based on that, we are going to work on this particular algorithm. So, talking about this BB84 protocol, we have separated out all the algorithms into the 7 steps so that we can come to know how this particular algorithm works each step by step, right? So first one is a preparation step where the sender is trying to prepare some kind of photons and assign some polarizations and everything. He does the preparation and then he sends that particular information or that particular data to the receiver, right? In the transmission phase. In the measurement phase, the receiver measures what exactly the data is received, and based on that, it does some kind of operations. Then, with the negotiation of the sender and receivers, the basis reconciliation is going to be happen. And after this reconciliation, the key shifting is done. Then later on, it is trying to detect the error detection or error corrections one, and also it is trying to detect whether any if eavesdropping or someone has tamping your information or not. And then after this particular detection, the privacy amplification has been done. So we'll see this all particular steps one by one. First one is our the preparation phase. Okay. So before going for the preparation phase, we must have to know what all are the types of the polarization and which kind of a polarization we mostly use in the you can say the this basic quantum cryptography, right? So polarization can be broadly categorized into two types. One is a linear polarization, and the another one is elliptical polarization. Now, most of the quantum cryptography algorithms we use are using the linear polarizations only. Right. So in the linear polarization, we have another one is rectilinear and another and a diagonal. These are the two different types. And the subtypes of this rectilinear are the horizontal and vertical. And for the diagonal, we have the diagonal and anti-diagonal. These are the sub types of the diagonal basis we have. Right. So most of the time in the in the BB84 algorithm and E91 algorithm, we use whenever it requires, we use the linear polarization. This particular concepts. Okay. So simply, what we have the polarization can be categorized into two: linear and elliptical. And linear can be further categorized into rectilinear and diagonal. rectilinear can be further categorized into horizontal and vertical, and diagonal can be again re-categorized into diagonal and anti-diagonal. So mostly focus on these rectilinear and diagonal polarization concepts, because these are being used further in the algorithms. Okay. So next one is in the preparation phase. What Alice will prepare a sequence of quantum states, that is your photons, to send to a Bob. Right. She uses two sets of polarization basis. One is a rectilinear, as I said, rectilinear and diagonal basis. So mostly rectilinear, in the rectilinear basis, we use horizontal and vertical polarization, and in diagonal 45-degree, that is the diagonal and anti-diagonal, right? So here are some pictorial representation. What we can do is, if you want to mostly represent binary 0, then 0 degree, binary 1, 90 degree. This represents the diagonal. This represents the diagonal. This and this one. These two, the blue lines, you can say, these represents the diagonal basis, where we have the 45-degree and 135-degree polarizations one. And the binary 0 can be represented as the horizontal or rectilinear basis, and 90-degree can be represented as the vertical or the rectilinear basis. Right? So in short, here we have given some rectilinear basis and the diagonal basis. Okay, so first two things are clear, like the polarization, linear and electrical. Mostly we use a linear, and here in the preparation phase of BB84 algorithm, what we do is we use the polarization for the photons, right, which we want to send to the Bob, and these polarizations are based on these two categories, right, like rectilinear basis and diagonal basis. Okay. Now consider here each of these polarization states represents the binary value, right? Just like here in the previous one diagram, what I shown, like 0 degree can say binary 0, 45-degree binary 0, but it is a diagonal. Binary 1, 90 degrees, but it is a rectilinear basis one, and here we have the binary 1 as a diagonal basis one, right? So similar, based on this, suppose we have represented horizontal as a 0, vertical as a 1, diagonal as a 0, and anti-diagonal as a 1, right? I can compare this one things with all of this particular polarization, photon polarization. You can find the same. Okay, so the sender what initially does, he first of all finds out these values, or default these values might be present. So for every photon, what the LS will do, LS will choose the random basis one. It will choose the random basis. Hello. Yes.
Sorry to interrupt. Actually, what about remaining angles, sir? If you have 45, you are taking. What about 55 remaining angles also?
No, see,
only 2 are fixed. No?
No, see. If suppose this is I can say the x-axis, right? X-axis. So x-axis, this will be again, it will be 0. Right? If it is a y-axis, then it will be again a 0. If it is if it is y-axis, it will be 1. Right? If it is in this particular direction, then it will be again a 0.
No.
It's
Yes,
just
actually 0 to 90.
Mm-hmm.
0 to 90, we can take like how the remaining angles also is there, sir. Like 30 degrees,
Mm-hmm.
70
Yeah.
degrees, 60 degrees. How can we take like
Exact opposite. Not exactly. We can say this is a 0 degree and 45 degree. Might be there are something like 34 degree, 35 degree, right? So most probably it will be get considered as a 45 degree, or it will be considered as a 0. This is just an example we have given, right?
Okay, sir.
This can be this can be extended to, if suppose we want to make a sphere and we want to go through this way also, right? Something like this, right?
Yes, sir. I got it.
So it can be made it as a 0. So this is just an sample how we can able to start with this one, right? Any queries up to this one?
Yes, sir. Clear, sir.
Okay, thank you. So, okay. Now when Alice want to send the data, or Alice want to start to send some data to Bob, and they want to establish a secure communication. So at that time, initially, what Alice will do, it will choose a random basis, right? That random basis might be a rectangular or diagonal, or it might be a mix of both the rectangular and diagonal, right? And what this Alice will do, Alice will randomly assign the binary values 0 or 1 and polarize the photons accordingly, right? That means that particular photons will be get polarized according to what the basis the Alice has chosen, right? So I'll move to the next one slide. Okay, so back to the preparation phase. She has been this has been done by Alice, and Alice has to choose a random basis, might be rectilinear or diagonal, and she has to assign the binary values for 0 or 1 and polarize the photons accordingly, right? So suppose here Alice has chosen or selected some random polarization basis and bit values for each photon. So in this particular example, say we'll use 8 photons. So like 1, 2, 3, 4, 5, 7, 6, 7, 8. These 8 photons. And Alice uses the basis R is rectilinear, D is a diagonal. So something R D something. This Alice has chosen the polarization basis one, right? And according to that, she has assigned the bits like 0, 1, 1, 0, 1, 0, 0, 1. And as I said, the photon polarization here is horizontal uh, for the rectilinear, or for diagonally, it is uses 1 and it is anti-diagonal. And similarly, it will uh, use this for all 8 bits, right? So here Alice's choice is what? It uses a basis that is a rectilinear and diagonal, and the bits here use 0 and 1, right? So remember that we are using the 8 photons over here. So, and any doubts up to this one? Any doubts or queries up to this one? Did you get understood what exactly this particular table it is?
Yes, sir. Yes, sir.
Okay. So R and D represents what? It's a rectilinear or diagonal. And here we have seen also the horizontal, vertical, diagonal, and anti-diagonal. These are the 4 photon polarization states, right? Now this preparation phase is completed. Now we'll move for the transmission phase. So Alice, after preparing this all 8 photons, what she will do? She will send that particular uh, photons to the Bob through a quantum channel, right? Since the transmission involves quantum states, any measurements by an eavesdropper will disturb the photons due to the measurement disturbance principle. So this is another one measurement disturbance principles we have. We'll see that particular disturbance principle later, right? So in this particular phase, what Alice will do, Alice will send that particular photons to Bob only, right? Now it's turn to Bob. What he has to do. So Bob, what will do? He will choose the random basis, random polarization basis R or A, that is rectilinear or diagonal for each photon and measure the polarization, right? So you can see the Bob's choice for the first photon. He has chosen the diagonal, then he has chosen then rectilinear, then diagonal. He has to choose any random basis, right? Now, with this particular random basis, we need to find out uh, the measurement result. All right. Now, here you can see what the Bob has sent. Sorry, Alice has sent. She has sent 0, 1, 1, 0. Right. What is going to be received here? The Bob has received something different. Right. Here also it has been different. Might be here Bob has received 1, 0 something. So that's why what we're going to do is we are going to discard the basis mismatch. Right. Now this process will continue and it will find the correct one which we need to keep for the basis or keep for the match. So this will be done in the next one step. But from this particular side, you just understand that Bob has received this with his random basis. He has received something random value or unknown value or the exact opposite value or what the Alice has sent. But currently we don't know what Alice has been sent, right? So that's why I just kept written here as a random one. Here we don't have any confirmation. Here also we'll check with the next one phase, right? So just remember here what the Bob has to do. He has to choose a random polarization base and he has to receive that particular, or he has to check with the photons, each photons, and measure the polarization. If it passes through that particular detector polarization, then photon detector, then it will be given as a 1 or 0. Okay. Now after measurement, here the part comes of the basis reconciliation. So Alice and Bob communicate over the public classical channel to compute the basis they use for each photon. So what first of all Bob does is Bob tells the Alice which basis he used for each. What happens? Bob tells Alice which basis used to each measurement. Now see what here Alice has sent RD, 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 RD. These are the eight photons that she has sent, right? And here, Bob has chosen his own random the basis, that is DR, RD, RRDD, right? So here, Alice and Bob should have to communicate over the public classical channel to compare the polarization basis for both Alice and Bob. So Bob tells Alice which basis he used for each measurement, what all are for the measurement, what are the polarization basis he has used. And Alice confirms whether the Bob's basis matches her for each photon or not. Right. Now, these three steps, one is Bob tells to Alice whether which basis is he used for the measurement. But most importantly, he does not have to share the measurement results. So what all are the measurement results for the Bob is these all measurement results. Whatever, whether it is a random, whether it is 1 or 0, this particular results it is not necessary to share with the Alice or through over the public network, right? So this is we are going to keep it as a secret, right? Then Alice confirms whether the Bob's basis polarization basis matches with her each photon. They discard all the measures where their basis didn't match, right? So it will that means which one basis will be get discarded, this will be get discarded, this will be get discarded, this will be get discarded, and lastly this will also get discarded, right? Discard all the measurements where their basis didn't match, retaining only the bits where the bases are aligned, right? That means here how many bits were there? 1, 2, 3, 4. These bits we are going to retain, and along with that their polarization basis also, right? Whether it is a rectangular, diagonal, rectangular, and diagonal, right? Understood up to this one? Any questions up to this? Hello?
So the question is, how do Alice and Bob actually share the information about their basis? Do they really talk? I mean, what kind of information exchange is happening?
This is again it can be happen on the public channel one, not a quantum channel or on any secure channel one. Even if
But then
suppose
that is also vulnerable, no? If the Alice Bob information about that thing has got in, it becomes sort of eavesdropped, then what?
no, that is also that's why here Bob is not going to share what the measurement result it is, right?
Right. Okay. Yeah, that's good. That's good.
That's why the measurement results were not going to be shared. But if suppose the measurement results are also getting shared, then that is again problematic one, right?
Yeah, I get that. That's a good one. That's a good point.
Yeah. So after the this whole picture is now what the Alice has sent and just a minute. What Alice has sent and what Bob is having a basis, and what all are the things we need to keep, and what all are the things we need to discard, right? Alice has used the rectilinear, and Bob has chosen the what I can say, the diagonal, right? That's why it is being get discarded. Something similar might be happened here, D and R, that's why it may be discarded. And here rectilinear, and that's why it is been kept. And the bits are being shared one, like 1, 0, 1, and 0, right? So these all are the matching basis one, or you can say the matching polarization basis for Alice and Bob communication, right? Now this matching basis, polarization basis, this 1, 0, 1, 1, we can call it as a shifting key or raw key one. This 1, 0, 1, 1. This is mostly we can call as the raw key. The bits corresponding to the matched basis forms the raw key. Okay. Now here again, the error detection and correction may not only with this particular stuff while sending the photons from transmitting the photons from Alice or Bob is happened. Might be this is due to some the noise in the channel or imperfect equipments, or might be some may have some other reasons also. But what we want to ensure that in this particular algorithm, that we whether we have get tampered with someone else or not, right? So to ensure the key has not been tampered with, what the Alice will do, Alice and Bob publicly reveal the random subset of their raw keys and compare the bits. So currently what we have the raw key as this one. We'll prepare the subset of this raw key and will publicly reveal with Alice and Bob, right? And then it tries to compare the bits one. If error rates is exceeded tolerable, or if that particular error rates are above the threshold, then they can conclude that the eavesdropping has been occurred, or might be it has been occurred, or this is not we can say directly the eavesdropping. This might be due to the noise in the channel or the imperfectment of equipments. But mostly with this one, we can conclude that the eavesdropping has been occurred, and the protocol is need to be abort, and we need to restart the process of key generation, right? If the error rate is acceptable, they proceed. They can then proceed with the next step one, right? If it is up below to the threshold, then it is acceptable, and it can be go for the next step one. Okay. So here error correcting algorithms. I think in the last one sessions you might have seen the error correcting algorithms like SQL protocols are applied to reconcile any discrepancies due to the noise in the channel or imperfect equipment. So here, regarding this particular algorithm, we need to consider only these points, that the Alice and Bob publicly reveal the random subset of their raw keys and compare the bits one. Okay, if it is above to the threshold, then we need to stop, or we need to abort this particular protocol and restart with the key generation. And if it is below to the threshold one, then we can if it is acceptable, then we can proceed for the next step one.
I have a question here actually.
Yeah.
So the threshold that we are talking about, has it something to do with the size of the key? Because the size of the key is very important in terms of how much data one should the length of the key. So if the length of the key is not sufficiently reached by the time they have made a transaction, then it is still compromisable.
Yes. No, even see, if suppose we have we are working on the 8 photons or 4 photons, then that again that will be not a good idea. We need a more you can say the more number of a key size one, and based on that the threshold is getting calculated. We do have
right, yeah. So that's why like we needed like more than something like 150, 200 photons per minute or something rate at which you can do, or even better more than that.
Yes. Thank you. But this is we have taken this is just an example to understand everyone what exactly this is to be done, right? Okay. So talking next is a privacy amplification. So here, even if AV, that is eavesdropper, has gained some partial information, say for example 30% or 20% of the information about the Rocky, due to the noise or error corrections or anything, something might be happened, right? Then Alice and Bob can perform the privacy amplification, right? So what exactly this privacy amplification is? They use the publicly agreed upon the hash function in any of the hash function, and to shorten the keys one, and it will reduce the AV's information near to the zero, not exactly the zero, but near to the zero, because whatever the key information AV got, right, or we can say the eavesdropper has got, right, that raw key information, that again what we are going to do is we are going to apply some hash function and we are going to create a shortened keys one, right? The resulting key is a final secret key which can be used for the secure encryption. That key can be used with either the one-time padding, this particular method, or a symmetric key encryption algorithm, right? So we'll see how this privacy amplification can be done more by using the hash function one. So here is just an example of a simple hash function. In the last one example, what we got the raw key as a 1 0 1 1, right? So here we'll apply one particular simple hash function, alias, and which obviously the sender and receiver is agreed upon that particular hash function, and this hash function will take a 4-bit input and produces a 2-bit output, right? So say for example I'm doing the x1 and x3. Hello? Yeah. XORing with the x1 and x3, XORing with x2 and x4. This is a simple the hash function we have, where x is what consisting of the rock is x1, x2, x3, and x4, as we have seen here. Okay, so x1 is equals to 1, x2 is equals to 0, x3 equals to 1, and x4 equals to 1. Now, how this particular hash function will be get evaluated? It will be evaluated by XORing the 1 XOR with 1, 0 XOR with the 0, and it will be get evaluated 0 and 1. So your final secret key will be 1 and 0 and 1. And this particular key we can use for the one-time pad or the symmetric encryption algorithms. So this, as I said, this one-time pad or the symmetric key encryption algorithm like AES or encrypt the message or encrypt message securely, we use this particular. So I think up to this everyone understood, or do you have any queries or question doubts?
Myself, Dr. Prem Kumar from Jain University.
Okay.
Yeah. So regarding key generation, like charge-based techniques now people are using for mathematical modeling to generate the secret keys and all, right? So for that, like I talk about here in this platform, we need to convert that mathematical equation into wave function or what? For example, say like we can take up a logistic map or a sign map or something like a mapping techniques. So by using that, generally like they are generating the keys. So in terms of like now people are doing for 3-dimensional, 4-dimensional, 5-dimensional, even 6-dimensional, keep on moving on that. So I want to know, like in this platform, how we can able to like convert those equations and all, whether we need to convert the mathematical modeling into wave function, and then we can generate for the same or what?
See, as per my knowledge about this cryptography, we don't have any scope to work on the mathematical equations, right? The last one, the privacy amplification. In this particular phase only, we can able to use some kind of a functions or some kind of a mathematical equations to shorten that particular keys. Because that keys might be someone has got the partial information about that particular keys. So here in the previous one steps, we don't have any scope to work on the mathematical equations or the functions. But here we can have some kind of a scope to work on the mathematical equations or the functions or formulas or some kind of algorithms. From through that we can more secure the privacy amplification particular process.
Thank you, sir. I think fine with the answer. Okay, thank you, sir.
Okay. So here major advantages of BB84 is eavesdropping detection, and it is not required to pre-share the secret keys as we do in this symmetric key cryptography. It doesn't require to need a prior shared keys for the secret. Then it has some kind of the limitations also for this algorithm, that is the distance constraint, and mostly this is the limitation for the quantum computing also, quantum cryptography also. Losses in the quantum channel limits the range of BB84, and current limitations can only achieve secure communication over the 10 to 100 kilometers only. This is just a limitation, the distance limitation for that. And is again depends on what kind of the quantum network or quantum channel we are going to use. And here we have the implementation challenges. It requires high quality single photon source. This is again difficult to have the single photon source with the high quality, and most important are the detectors. At the receiver side, we want strong detectors which are difficult and expensive to achieve. So basically, these two limitations we have with this particular algorithm. So here we have for the BB84, we have the different variants one, or we can say the improvements one, decoy state BB84, which will improve the security and efficiency using the multiple photons, photon intensities to detect the photon number splitting attacks one. And second one is device dependent QKD. So again, talking about the device dependent, it will be a little bit costly one, but it will ensure the some better security one. So finally, talking about the this is just an algorithm. I just want to show you or represent you in front of you. Overall, we are going to talk about the benefits and challenges of quantum computing. We have a lot of benefits over here, but regarding quantum cryptography, major two benefits are unhackable communication. This is theoretical one proven, but and detection, the temper detection. And the challenges is obviously we need a high cost for the infrastructure setup and providing the communication channel. Then we have the infrastructure limitations and scalability issues. Again, horizontal scalability, vertical scalability, this might be more challenging one in case of quantum cryptography. So might be you all aware that in these kind of the applications, banking and finance, government and military applications, healthcare, and the relevant industries where the information is more secure, and we need to keep the information more secure. And this particular areas we can use this particular algorithm, and again obviously in the quantum networks also we can use this applications. So talking about the future trends in the quantum cryptography, we have a lot of in the future development or future advancements. That is, we can integrate the quantum cryptography with the our classical cryptographies, like what we do in the post-quantum cryptography. This can be a good addition or the future advancements we can able to do. And some of the future enhancements or the challenges we can take into the considerations, which is posted by the quantum computers. Right. So this kind of the future trends we can take into the considerations for the quantum cryptography. And that's just a simple quiz. What is QKD? Anyone can give me the answer for this one?
Quantum key distribution.
Yeah, good. Then simple principle of detection of eavesdropping.
No cloning.